Hello. So hopefully by now you've seen some examples, some demonstrations of how gas laws affect the behavior of gases in everyday things, and some of the ways that we can kind of look at how changing one factor maybe affects one or more of the other factors. Changing temperature might affect pressure or volume. Changing pressure might affect volume. Changing volume might affect temperature or pressure. Changing the number of moles might affect all those things. And so what we're looking at, again, just to remind you, is that these are various applications of the ideal gas law. And we've already worked with the ideal gas law a bit. The equation that we use all the time there is PV equals nRT. And it has all these variable parts in it: pressure, volume, moles, and temperature. And then it has that key here. Remember that R is the ideal gas constant. And sometimes we forget that this ideal gas constant is a constant. And what that means is it's the thing that won't ever change. It's the thing that won't vary while the other things around it can all change, can all vary. R is a constant. And if we rearrange this equation to get R by itself, R is PV over NT, right? If I take this equation to get R by itself, I would divide both sides by NT. And that would give me, as those N and T would cancel out, R equals PV over NT. So what this is saying is that no matter what we do on a particular gas sample, if we change the pressure or the volume, the number of moles or the temperature, something else, the pressure, the volume, the moles, or the temperature, will have to change. Likewise, it'll have to change to compensate for that, to keep R constant. R can't change. So if I increase the temperature, then something else will have to change in order to kind of keep with it. I'm having trouble with my pop-ups here. But as temperature increases, let's say volume will have to increase. And we see that with balloons, say, put in a freezer. As temperature goes down, volume has to go down. And the reason why that has to happen is because in order to keep R constant, right, something's going to have to give. As temperature goes up or down, volume might have to go up or down to go with it. As temperature goes down, maybe pressure goes down. We see this with car tires in the wintertime. The pressure on your car tire will go down on a very cold winter day. You might visibly see it. You might not. You might see it. You might see it visibly when you look at your car parked, or you might just notice that you have a pressure sensor go off on your dashboard or something like that too. Okay, so as we look at the relationships between these, the idea is that R will always stay constant. And what we can get from that, what we can kind of take from that is that no matter what the conditions, the before or after conditions, if a pressure changes, a temperature changes, something else will change to kind of go with it. Okay, and what that means is that the pressure, let's just take a little closer look at this, the pressure before we make a change, let's say, and the pressure after we make a change might be different, but something else around it will have to change with it. So we have before conditions, and we have the after conditions. And no matter what, R will have to be the same. So the pressure beforehand, we might call that pressure 1. The volume beforehand, we might call that volume 1. The number of moles, the temperature, in the before conditions, we label those with 1s. And then the afters, we might label those with pressures as P2, V2, N2, T2. That idea that the before and after conditions are going to vary, and as pressure changes from before to after, then volume will change to compensate for it. And what this gives us is that R staying constant will allow us to set these things equal to each other. And I've got this handy dandy equation right here. Taking the R and sort of throwing it out, since it's a constant, we can forget about it. It's not going to change anyway. And we can focus just on this equation. And it's big. It looks really big. It looks complicated, right? P's and V's and N's and T's, and we have lots of different parts going in front of us here. P's, V's, and N's and T's. But here's the good news. We don't work with all of them on every problem. In fact, we very, very rarely would work with all of them at once. We're usually able to take at least a couple things and sort of take them out of the equation because they too are constant. When something's constant, we can kind of forget about it, leave it out of the equation, and just focus on the things that are changing in the equation. Before we go on and start to use this equation, let's write it down. Take a minute, write it down at the top of your page, write it down in your notes. This is an equation that's based on the ideal gas law, based on keeping the ideal gas constant as a constant, and allowing the pressure, volume, moles, and temperature to fluctuate around that R. In order to keep that R constant, they change to sort of balance each other out. Okay? And so there's some give and take between the different factors: pressure, volume, moles, and temp. So P1V1 over N1T1 equals P2V2 over N2T2. It's actually kind of fun to say. The only things to keep in mind here with this is that temperature must be in Kelvin degrees or kelvins all the time. No exceptions for us to use this equation. The other thing to keep in mind is that volumes can be in whatever units you want as long as V1 and V2 are in the same units. Let's say that's milliliters or cubic feet or liters or cubic inches or whatever the unit might be. Pressure can be in whatever units you want. Pressure can be in atmospheres. We've seen a lot of that. It can be in other units as well. As long as the pressure P1 and pressure P2 are the same units, they can be whatever units you want them to. And there are many different pressure units. Atmospheres, pounds per square inch, like we see on a tire or a basketball or something. What we call inches of mercury. Inches of mercury is actually the unit that you'll find a lot of times if you watch the weather. They might report the atmospheric pressure in inches of mercury. Something like millimeters of mercury, which is kind of like inches except the metric equivalent. And why those units of inches of mercury and millimeters of mercury are pressure units isn't something we're going to get into right now. You just have to kind of trust that when you see units like inches of mercury or millimeters of mercury or PSI, that those are just pressure units, pounds per square inch, atmospheres, and there are lots and lots of other pressure units. All kinds of different areas of science and industry have different pressure units that they just like to use. And remember, N is in moles, which measures the number of particles, and then volume can be in lots of different units, most of which are pretty familiar to us. All right, so keep those things in mind as we work on some of the example problems here. And I'm going to work out 4 problems from your assignment and then ask you to work on some of the remaining problems, and that assignment's posted there with the details for you in Google Classroom, or you've been assigned it there to take a look. And I think it's going to be to complete most of the problems that are left. Right after this assignment, after the examples rather are complete, your assignment will be to complete most of the examples that are left. What I've kind of got in mind for you here is that I'll do 4 of these, and then that'll leave 13. I'm going to ask you to work on any 10 of those 13 that you wish to complete. So let's take a look at number 1. What I would encourage you to do as you tackle these problems is notice there's a lot of numbers in some of these problems, and then it's asking you for something as well. I would go through and sort of label them so that I keep track of what's what. So here in number 1, it's telling me that I have a pressure, a PSI, 25 PSI of pressure. I know that's a pressure. It's saying that at 25 PSI, that's my first pressure, so I'm going to call that P1. The volume of the tire is 1,800 cubic inches. Well, that's the volume at the beginning. That's the volume that goes with that pressure, right? You can just sort of tell in the way that the sentence is structured that that pressure goes with that volume. Now, the second part of it says normal volume for the tire is 1,500 cubic inches. So that's another volume. We're going to call that one V2. And then it asks, what is the correct pressure for the tire? So what is the correct pressure? That's what it's asking us. It's asking us for the other pressure. It's asking us for P2. Normal volume, normal would be like the correct pressure if your tire was properly inflated, right? So I have P's and V's, but what about the N's and the T's? Remember our equation here, I'm just going to jot it down at the top, is P1V1 over N1T1 equals P2V2 over N2T2, right? When we have pressures and volumes like we do in question 1, and we don't have any mention of N's and T's, of moles and temperature, that means we can just leave it out. So I'm going to take that equation, I'm going to write it one more time, P1V1 over N1T1 equals P2V2 over N2T2. I do like saying that equation. And I'm going to cross out the things that I know aren't important in this problem. Because they didn't mention moles and they didn't mention temperature, we can treat those as being held constant, and we can just leave them out. So I'm going to leave out moles and I'm going to leave out temperature. And what does that leave me with? That leaves me with a nice, simple P1V1 equals P2V2. Now that's not such a big, ugly equation. It's only got 4 parts. And if we look at the information that they gave us up above, they actually gave us 3 out of the 4. We just need to find the 4th one. It means kind of plugging in numbers and rearranging it by algebra to get the right answer. So let's plug in what we know. P1 is 25 PSI. I'm going to go ahead and put that in there for P1. V1 is 1,800 cubic inches. I'm going to go ahead and put that in there for V1. You can write it in however you want. Cubic inches would kind of look like that. Inches cubed or cubic inches. the normal volume is 1,500 cubic inches. What's the correct pressure? So they're asking me to find P2. That's my unknown. That's like my X, right? And then 15, whoa, I got a funky telltale here, PSI. I'm going to fix that up. Okay. The V2 is given as 1,500 cubic inches. So I know 3 out of the 4 parts, right? That's pretty typical on these. I might know 3 out of 4. I might know 5 out of 6 on some of the bigger problems. And I'm looking to find that one that's left. So here to find this by algebra, pretty straightforward. I want to get P2 by itself. I'm going to divide both sides by 1,500. And I'll take those units along too. It's good to do that. Make sure those units come along just so that they cancel out. This will all cancel out on this side, right? Algebraically speaking. Inches cubed or cubic inches will calculate or cancel out rather on the left side. And that'll leave me with units of PSI. So that's the units that we want. That's a pressure unit, so that makes sense, right? And if I go punch this in my calculator for number 3, 25 times 1,800 divided by 1,500, I should get a P2 of 30. And remember, the units on that are what was left over. What units didn't cancel out? Again, that's PSI. Okay, 30 PSI. That's my answer, P2. What's the correct pressure for the tire? 30 PSI. And so, in the end, most of the time on these problems, you should be able to treat some things as constant, cancel them out like we did from the big original equation, and then go ahead and plug in the information that's given to solve that problem from there. Think about one last little thing. Think about on this last problem. Does it make sense to us? If a pressure on the tire is at 25 psi, I stick my pressure gauge in my tire and it's at 1,800 cubic inches, it says 25 psi. If I get that tire volume down, right, to 1,500 cubic inches, the gas in that tire will be at a greater pressure than it was when it was at 1,800 cubic inches, right? Because the same number of moles, there's no gas leaking out in this story. So all the particles are still in the tire, but I'm making the tire smaller by 300 cubic inches. I'm making the tire quite a bit smaller. And if you make the tire smaller and the same number of particles are staying inside, those particles are going to have less room to move about. They're going to bump into the walls of that tire more often, and they're going to exert a greater pressure on the inside of that that tire. So it makes sense that if I force the tire to a smaller size, the pressure inside that tire is going to be a greater pressure than it was before. So the pressure is sort of expanding here. The tire, it's not a proper size, not a proper pressure. In order to get it back to its normal volume, the pressure would have to have maintained at a greater volume, or a greater value rather. All right, let's look at number 3. What temperature is needed to change 150 milliliters of oxygen at 20 Celsius to 200 milliliters? Let's take a look at what they're giving me here. What temperature? Right away, I know they're looking for a temperature. I'm not going to label it just yet. I could, okay, but I'm going to wait, and you'll see why. It also tells me there's a volume here. I'm changing 150 milliliters, that's a volume, at 20 Celsius, that's a temperature. Now, I want you to notice something here. When you see that word at in there, that's an important little preposition. That's going to link the value to the left and to the right. Almost every single time, it's as simple as that. So the volume and the temperature that are linked by that word at, 150 milliliters at 20 Celsius. That means that volume and that temperature need to go together. I don't care if you call them V1 and T1 or V2 and T2. It doesn't matter as long as you link them together and call them either both of them are number 1 or both of them are number 2. And mathematically, it won't matter which one's which. And then it says we're going to change 150 milliliters to 200 milliliters. Well, that's my other volume, right? That's my second volume. And so that means that they're looking for this second temperature, right? It's over here. And think about it, it kind of makes sense. What temperature is needed to get to 200 milliliters? What temperature will it take to change that volume to 200 milliliters? So it kind of, by putting them at the other opposite ends of the sentence here, it seems a little funky kind of, but it's sort of linking that temperature and that volume together, right? Just the way that the sentence is structured. So the temperature, the second temperature or the other temperature is the one that we're looking for here. If I take my equation again, P1, and you don't need to rewrite the equation every time. If you can kind of eyeball this, you go ahead and do it. I'm just going to do it for the sake of our examples a little bit more thoroughly, as I like to do. Okay. What's involved? We've got temperatures and volumes. So that can mean that for our purposes here, the pressure isn't mentioned, so the pressure is staying constant. I'm going to leave pressure out. And the number of moles isn't changing. Apparently there's no oxygen leaking or being added to this sample, so the number of moles is staying the same. I'm going to leave N out. And that leaves me with what? That leaves me with V1 over T1 equals V2 over T2. That's the equation that's left once I've canceled out those things that are being held constant. Now remember, the only rule we have, really, that's a real hard, fast rule, is that temperatures have to be in Kelvin before we can put them into this equation or any other equation using temperature in this way. And so we have to have that temperature in Kelvin. And remember, the difference between Kelvin and Celsius is 273. Kelvin is Celsius degrees plus 273. So I'm going to take that 20 Celsius and I'm going to add 273 to it. That's 293 if I treat it in Kelvin, right? If I treat it in kelvins. That's my T1. T1 is 293, not 20 Celsius. I mean, it is, but we're not going to use it as that in our math. We're going to use it in the Kelvin form. So I'm going to go ahead and plug that in down here. V1, 150 milliliters. T1, we now looked it up, did a little conversion, is 293 Kelvin. Let's stick that in down there. All right, V2, 200 milliliters. T2, what I'm looking for. Okay, that's my unknown piece over here. Take a look at this. If I'm going to raise the volume of this gas, that means it's going to have to get bigger and expand. That means I'm going to have to heat it up. So the temperature I'm looking for is going to be something greater than 293. Just going to have sort of a sense in your head of what's a reasonable answer here. Well, for the volume to go up, the temperature will have to go up because that'll cause a gas to expand. All right. If I do the cross multiplying and dividing here, I'll get that answer. But let's just take let's take a moment. Pardon me, my yawn. Take a moment to actually set this thing up. So I'm going to do the cross multiplication. I think that's helpful for a lot of folks to see. So go ahead and work that out. If I cross multiply, I get 293 Kelvin times 200 milliliters equals 150 milliliters times T2. And the reason this is important to do is a lot of folks will just kind of go to their calculator and plug in those three numbers in some random manner and just hope they get it right. And 2 times out of 3 or 3 times out of 4, they won't get it right. There's lots of different ways to plug that into your calculator and not get it right. There's really only one effective way to get it right. So if I cross multiply and actually don't really do any math, I just cross multiply and move the terms, this is going to get my T2 by itself. Not quite, but I can divide by 150 milliliters on both sides now. And that will cancel out my 150 from that side and leave nothing but T2 on the right. It'll cancel out my units of milliliters over here, and now I go to my calculator as 293 times 200 divided by 150. And I should get an answer of T2 equals 391 Kelvin. Okay. Now that's in Kelvin, 391 Kelvin. The question doesn't say what units it wants. If the question said what Celsius temperature, then you'd need to go back and subtract 273 again, right, to get it back to Kelvin, because this is in Celsius and we'd have to convert it back. So if this question asked for Celsius, we couldn't just leave the original one in Celsius and get an answer. We have to convert to Kelvin, do the math in that equation, and then convert back to Celsius. I know it feels round and about and lots of extra work, but that's just the nature of gas laws and the math that we're doing. So if I was to take 273 away from 391, if I needed to get back to Celsius, or if I just wanted to, if I took 273 away, that would be 118 degrees Celsius. So either one of those would be correct here, since it doesn't specify what units it wants. All right, let's take a look at a couple more. Number 6. 6 gives us quite a bit of information. It's saying we've got a gas here with 894 cubic feet. And again, cubic feet, that's a volume. So 894 cubic feet, that's my V1 of gas, is measured at 23 Celsius. So that's my T1. And 29.9 inches of pressure. That's my P1. Remember, that's one of those pressure units I mentioned at the beginning of the video. So I've got V1, T1, and P1. Calculate the volume of the gas. So they're looking for V2. I don't know that one yet. Calculate the volume of the gas at 45 Celsius. There's T2. And 18.7 inches of mercury. That's P2. And again, don't get wrapped up in understanding inches of mercury. If you're curious about it, you can read about a device called a manometer, which is spelled manometer. if you're really curious about that pressure measurement and how manometers or manometers help us to get something like inches of mercury. But they're kind of by now they're kind of an antique tool. We don't work with them much directly unless we're in a very specific area of science where we have to be like deliberately using those devices. There's a lot more convenient ways of measuring pressure now, so they're kind of an antique tool in a lot of ways, but they have some really cool roots and a neat history. But here's an equation to solve with 6 pieces, right? We have V, T, and P, and we have V, T, and P. So there's 6 different variables going on. So once more, let's go back to our equation. P1 V1 over N1 T1 equals P2 V2 over N2 T2. And remember here, what can we cancel out? Well, the only thing that's not mentioned in my numbers that were given is the n's. There's no mention of moles. So they're constant. They're being held constant. So I can take the n's out. Now, instead of rewriting it, this time I'm just going to erase them. And there's my equation. So I've got P's and V's and T's. Let's plug it in. Remember, we need Kelvin temperatures. So before we can plug them in there, we'll have to turn those Celsius temperatures into Kelvin by adding 273. So make sure to do that. On the one side, on the left side, I've got P1, 29.9 inches of mercury. I've got V1, a volume of 894 cubic feet. That's a pretty significant volume. And I've got a T1 of 23 Celsius, which when I switch to Kelvin is 296 Kelvin. Again, add 273 and I've got it. On the other side, my pressure, my P2, is 18.7 inches of mercury. Remember, those pressure units can be kind of whatever as long as they match. And here they're both in inches of mercury, so that's a match. The volume is what we're looking for, so V2 is my unknown part here. And then T2 is 45 Celsius. And again, in Kelvin, we need to get that to Kelvin, is 318. 318 Kelvin. All right, so we got a lot of parts going on here. I need to get V2 by itself. Right. Now, if you prefer, and you can always take the equation that we have here on the left, right? We can always take this equation and actually get the V2 by itself beforehand if you like to do that. A lot of folks prefer to do that. I'm not sure if you've just determined for yourself yet if you have a strong preference or not, but I like to do that actually myself. I'm not sure. In this case, I haven't done that when I've been rearranging these, and maybe I should have, but the algebra works out about the same, whether you rearrange in advance or if you rearrange afterwards. But if I want to get V2 by itself over here, it's in the numerator, so that's a good sign, right? To get V2 by itself, I'm going to multiply both sides by 318 Kelvin, because that'll cancel it out right on this side, and it'll get rid of it on the right. It'll move it over to the left. And then I'm also going to divide both sides by 18.7 inches of mercury, because I want to get rid of that on the left. And it's in the numerator, so I'm going to divide. And over here I'll divide as well, put it on the bottom, 18.7 inches of mercury. All right, and that'll cancel it away from the right-hand side. Now I've got 5 variables on the left side of my equation here. I've got 5 pieces of math here, 5 numbers. But before I go punching all this into my calculator, let's check the units canceling out too. That's going to help us. Kelvin's going to cancel kelvins. Inches of mercury, my pressure units, those are going to cancel out. And the units that's left here will be cubic feet. And we're looking for a V2, right? We're looking for a volume, so that makes sense. If you go to your calculator and punch this in carefully, 318 times 29.9, right, times 894. That top term, I would put that into one parenthesis, and then divide it by the bottom term in one parenthesis, 18.7 times 296. One top term in a giant parenthesis divided by a bottom term in a giant parenthesis. Highly recommend that's how you'd set that up. And if you do, V2, it should come out to be right around 1,536, if you did the math right, cubic feet. So there's our V2 on number 6. All right, so quite a bit going on that one. But other than getting Celsius to Kelvin, it's just kind of handling and manipulating those variables, getting them by themselves. If you're not quite as comfortable with putting those numbers in and moving them around, like I mentioned, you could take the equation itself. I'm just going to kind of move it here, I think. Move it down and show you how you could rearrange the original equation here. Okay, I'll take that equation, kind of bring it down to the bottom, and just kind of play with it a little bit here. In case you haven't, you worked with it this way before. If I wanted to get V2 by itself, since I've figured out that that's what I'm solving for in this problem, if I wanted to get V2 by itself, and I'm just going to make it blue so I can kind of isolate it here, I would do what we just did maybe with the variables before I even start. Right? So What I mean is multiply both sides by T2, and that'll cancel it out of this side, right? And then we divided both sides by that pressure. Well, we divide both sides by P2. So P2, goes on the denominator on both sides. That would cancel out P2 on this side and move it to the other side. And what do I really have right now? If I rearrange the equation, I have V2 equals T2 P1 V1 over P2 T1. Now sometimes that's intimidating to people, all these different variables here, but that's the same thing that we just did in variable form. And this way you could just bring down all those 5 values, which were all given to us up here in the original equation. They gave us all 5 of those, plug them into those positions in that equation, and then punch it in. You'd be doing the exact same math that you just did here, top terms divided by bottom terms. It's just that you wouldn't have to move numbers around in order to get it by itself. You just move the variables around in advance and then get the variables set up that you wanted all alone, plug in some numbers and go. All right, let's do number 11 and then we'll be finished. And I chose 11 because I wanted to do one where we solve for moles. It says we have 0.85 moles of gas. That's our N1. And a volume of 20.5 liters. There's our V1. How many moles? So there's my question. N2, how many moles will be needed to get to a volume of 28.6 liters? There's my second volume. All I've got is N's and V's. So one last time, P1V1 over N1T1 equals P2V2 over N2T2. And you're getting really savvy at these by now, and you can recognize that pressure and temperature are not mentioned here. So I'm going to take pressure, and temperature, and take those out of the equation, and I'm going to have just V's and N's left, right? So with those things canceled out, I have V1 over N1 equals V2 over N2. What are we solving for? N2, right? You can get N2 by itself in advance if you'd like. I think with 4 variables like this one, it's probably not quite as challenging if you just put the numbers in and then move them around, but it's up to you. You can go either way. My V1 is 20.5 liters, so I'm going to go there. My N1 is 0.85 moles. My V2 is 28.6 liters. My N2 is what we're looking for. Okay, so there's my equation to solve. I kind of got a little low with it, so I'm going to get it up out of my way just a touch. Okay. If I want to get this by the N2 by itself, I need it out of that denominator, right? We don't want it in that denominator. So we're going to cross multiply. I'm just going to cross multiply and move terms. So this is going to be 20.5 liters, right, times N2, just by cross multiplying, equals, and I'm not going to go to my calculator yet, 0.85 moles times 28.6 liters. And I don't like to go to my calculator till the end, because if I do, then I kind of tend to lose track of my units, right? When I punch things in my calculator, the units get all kind of funky. I'd prefer to do it at the end and cancel units out before I start doing anything in my calculator, if I can. All right. So to get N2 by itself, now I need to divide by 20.5 liters on either side. 20.5 liters on there and there. And in doing so, it'll cancel it out from the left side. It'll leave me only N2 on the left. That's what we want. And on the right, my liters, my units of liters will cancel out. And so now all I'm left with is units of moles, and that's what we wanted. And if I calculate that, N2 should come out to be 1.19 moles. And that makes sense, right? I mean, at least in some way, the volume's going up. To get a volume that's greater, it's going to take more gas. If the pressure and temperature are staying the same, if I need to raise the volume from 20.5 to 28.6, it's going to take more moles of gas in that same balloon. In this case, going up to 1.19 moles gets the job done at the temperature and pressure that were described there, or not described there in this case. So that's the idea. With the questions that are left, there aren't really any in the ones that are left that are any different than the ones that we just did. You just have to go through and label what sort of information you're given with P's and V's and N's and T's. Figure out what's constant, take it out of the equation like we've been doing. And if it helps to write it out every time, great. Otherwise, get to this equation that has the things that you actually need for the problem in front of you. Plug in the ones you're given and solve for the one that's left with careful algebra and moving those terms around by the rules of algebra. Not the rules of chemistry even here, just the rules of good algebra. Work on the ones that are left. I want you to do 10 of the 13 that are remaining. Get your homework turned in by that due date. Check the details on Classroom. And I'll talk to you again. Let me know if you have questions. Pop in during office hours. I'm happy to help you. We'll take it from there. And have a great day. Talk to you later.